Configure router 2 as the NTP master and other routers as clients. Ensure that should link 1 or link 2 go down, all routers still receive NTP information. Let's begin by logging into router 2 at 172.16.1.2 and configuring it as the master. To configure router 2, issue the command ntpmaster1. It will work without the 1, but we want router 2 to be the highest source of truth at stratum 1. To configure the clients, issue the command ntpserver and the IP of router 2's interface, 172.16.1.2. Now, return to router 1 to check that the NTP is working. Issue the command show NTP status. Here, we see that synchronization has not occurred and router 1 is not aware of the clock. NTP is a cautious and slow protocol, and it takes a little bit to converge. This video is sped up, but I waited approximately a minute and a half to issue the command again. The second time, we see that router 1 knows of 172.16.1.2, router 2, as the reference, and synchronization has occurred. The show NTP association command is also a valuable command. It reveals that router 1 has selected router 2 as its time source, and that it's polling it every 16 seconds. The reach is an important attribute, and we want to see it increasing. 377 is the magic number. Remember this, it's going to be important later. Verify that the remaining clients are in sync with the NTP server, and then return to router 1. Router 3 was configured to use 172.16.1.2. So why is the reference clock 172.16.1.5? By default, the NTP server will send NTP replies out interfaces it receives requests on. Router 3 reaches the destination 172.16.1.2 via router 2's interface with IP 172.16.1.5, meaning replies are sourced from that interface. Log in using the network directly connected to the laptop. This means the IP 172.16.100.1. Once in, shut the interface towards router 2. This is the gig 000 interface. Issue the command to check the reachability to the NTP server. Looks okay, but remember, the NTP is cautious and slow. The poll time is now 32 instead of 16, as previously seen. This is because the poll time increases as the stability to the NTP is maintained. Wait approximately 33 seconds and issue the command again. Reachability has decreased, only by 1, so not too bad, right? Again, wait approximately 33 seconds and issue the command. It has decreased. This is expected as router 1's reachability to 172.16.1.2 was removed. Reachability will continue to decrease until it's 0. How can we avoid this? The answer is a loopback interface. Let's configure it on router 2. Return to router 1 and view the route table. Router 1 lost connectivity to router 2 on the 172.16.0/30 network, but it now has reachability to router 2 via the loopback IP. Change the NTP server to the loopback. Check the synchronization again. Interesting. Router 1 is now using 172.16.1.5. The reachability is increasing, which shows the success. Now referencing the loopback, router 1 reaches router 2 via the path through router 3. This lesson wasn't about NTP, but about understanding the usefulness of a loopback interface. For important services, if more than one path exists for the destination, as long as one remains up, traffic, destined for the loopback, will be successful.